All right, so especially since we have a couple of our friends sick at home today, or at home for whatever reason, maybe they just decided to skip. We're going to try to run through this really quick, hopefully like 15 minutes, so you still have some time to work on your homework. We're talking about proving triangles similar. Now, what's the difference between being similar and congruent, and what's the same? So we like those similarities and differences questions. So Michelle, give me a couple of characteristics.
So similar and different is like similar triangles are where they're like dilations, but they're not necessarily like congruent. Congruent is where absolutely everything is congruent, including the sides.
Okay.
Similar is just like the angles are congruent, but not necessarily the sides.
Yeah, so my angles have to all stay the same, but my sides are going to dilate. So you're either going to get bigger or get smaller by some dilation factor that's going to multiply to each of them. Now, the trick question they will try to get you to fall into is if they add something to every side. That is not similar unless there's very, very few situations where you could do an addition and or a multiplication. But normally, if you see that they've like added 5 to each side, that's not going to be similar because you can't add to each side and keep it similar. You have to multiply. So we know that if angle S is congruent to angle M and angle R is congruent to angle L, then my third angle also must be congruent because of the triangle angle sum theorem. So we know that if we see two congruent angles, we have similar shapes because, or in a triangle, because the third angles would also have to be congruent. Side, side, side is if I set up, or sorry, side, angle, side first, is if I have the side, then the angle between the sides. Now what's the problem with angle, side, side? Not just what does it spell, but what's the issue? Why does angle, side, side not work? Like we always tell you it doesn't work and it spells a bad word, but why doesn't it work? Yeah.
You can extend the third side without.
That's a really long 5. But if I have that angle, side, side, or like rotating my side inward, there are triangles that you can set up that share congruent angles and then the two sides, but they're not similar and they're not congruent. It's because you can flip the leg the other direction as opposed to coming in. You could flip out and just make a whole different triangle. So make sure that the angle has to be in between the two sides. And our last theorem is side, side, side. If they all share a standard ratio, then we see that they are similar. So let's look at question A here. So I'm going to zoom in a little bit. Using the angle-angle similarity postulate, how can we relate these two triangles together? Well, as they tell us right here, vertical angles, like I say, sometimes I do it out for you. So I would underline or highlight vertical angles, and then we can notate that these must be congruent. Since those are congruent, we don't need to put this, but I am. We also know that these must be congruent. So then, based off angle-angle, I have similar triangles. If I then know any lengths, I could figure out congruent triangles, but I don't know lengths. So we're stuck here. We have similar triangles. Any questions on being able to make that statement from an image like this? So shift over to the right a tiny bit. Sorry, for this to be on. All you did was miss the slide that had the date and the stuff. So try B. Are these similar triangles? Oh no, the cards. The cards.
Those are scary. They're actually
Carmen, what do you think? What did you start by doing?
I started by adding 90 degrees, 51 degrees, or well, I added 90, 51, and 31.
Where are you at? I said shift to the right to look at B. Carmen, Michelle?
So they're not similar triangles?
They're not similar triangles. How do we know this?
Because of the angles in a triangle, they add up to 180 degrees, and when you add up L and J, they add up to 100, so that means K has to be 80, and when you add up R and Q, they P has to be 25, and not all the angles are the same.
Yeah, so we are not similar here based off the fact that my angles are not the same. I have one angle that's the same, but I do not have two of them. Bless you. Questions? Did not think so. So now try your got it down there, Carmen.
Will you call me? Because I know the answer to this one now.
I'll call on you in a moment, yeah. No, because I already told Carmen that I'd call him. So Carmen, as we heard you saying, you said first I added the 90 and then we were all like, wait, what? So you said you added?
Excuse me, can I have Di Hunt to the office? Di?
Okay, so what'd you do, Carmen?
I added 90, 51, and 39 together.
What's that give you?
That gives me 180.
Ooh, so since these three added together give you 180, that tells me that this angle C must be 51, and this angle E must be 39, and then Carmen.
That means they're similar because they have all the same angles.
What do you mean it's not drawn to scale?
It's obviously lower.
I think just locating.
I know, but
No, but like
obviously.
FE and AC are obviously not.
And then DE is shorter than AB.
Don't trust what it looks like. Trust what you are told.
I'm just putting that in now.
Yeah. So always, if they give you numerical notations, trust what you're told, not what you see. You're not Megan? Thanks. So move on to the back here. If we can set up a similarity ratio and prove the ratios are the same for all three relationships, short to short, long to long, and then the middle, which they call our remaining side, we can prove the similarity. So this is if I don't have any angle measures and I do have only lengths and I have all of the lengths, we can set up short compared to short, long compared to long, and the remaining sides, as long as we make sure that we stack the same every time. Rhea?
I have the answer.
So, what's your ratio for the short sides? Which over which?
2/3.
Well, so what do the numbers start with?
Oh, 6 to 9.
6 to 9, which gives me 2/3. What about US to WX?
Oh, sorry, 10 to 15.
Which comes out to be
2/3.
2/3. And TU to TW?
8 over 12.
8 over 12, which comes out to be 2/3. Are these similar?
Mm-hmm.
Yes. So, same similarity ratio. They are similar. Cal, do you have a question?
I just don't get why you wouldn't put them in ascending order. Like,
Just how
the
they
lowest
structured
number
it.
to the highest number to the middle number.
Yeah, you can do it however you want to. So when I do this, I would honestly just do 6, 8, 10, and then 9, 12, 15, and you're asking, are these equal? That's what I do. I set up short, middle, long, short, middle, long. Are they equal ratios? If so, yes. If not, no. So, are our triangles here similar? Set up those ratios. And if you want to be like what Calvin suggested, just do our short, middle, and long all compared to short, middle, and long.
What triangles is asking us to?
KLP and KMN. Yeah, the one triangle is contained within the other, so be careful. So now I don't have all three sides. But what do I have? Max?
2 sides and the angle ratio.
I have a shared angle that comes between the sides that I've been given. So since it is an included angle, we could do side angle side if I show the similarity ratios for the two sides that I have. So I don't have a middle side. I don't need to use that now. I just need to see, are these two ratios equal with each other? Well, if I reduce my 8/10, it comes out to give me 4/5. Is that equal to my reduced 12/15? Yeah. Because if I divide by 3, I get 4. Divide by 3, I get 5. So since I see that these two similarity ratios are equal and my included angle, then we can say yes by side angle side. Then we have to write in the correct order. So this is where people were missing questions. Forget if I was on the Math 1 tests or here on our early Math 2 tests. If I start at K and then go to L and then to P, that has to be similar. Remember, no equal sign since we're just doing similar. Start with K, go the same direction, so M and then N.
So I made the mistake when I was setting up my ratios of doing the 8 to 12 and then 10 to 15. Is it just a freak accident that it came out equal? Or
What do you think? If how the shorter side compares to the longer side, will that ratio have to be the same as how the smaller triangle relates to the bigger triangle? So if we want to grapple with this problem, sorry, but if I gave you the easy answer, it wouldn't be as much of a learning experience. Let's set up our famous right triangle. And if I say famous right triangle, do you know what I'm talking about?
yes.
Or 3, 4, 5, right? So give me some blank paper. Come on. There, some blank. Ah!
You could just zoom in really, really far.
I did. I'm 800.
No, on the triangle.
Okay.
That's fixed.
So if I set up my 3, 4, 5. And we know that this is similar to any dilation of it. So let's do 9, 12, 15. So this is a dilation factor of 3, right?
Yes.
How the 5 relates to the 3, is that the same as how the 15 relates to the 9?
Because you multiply it times 3 over 3, which is 1.
So if the proportionality of the triangle stays consistent, will that ratio also tell us what we want? Because it's just telling me this side has the same relationship to this side as this side had a relationship to that side. They have to, it goes back to the trig, honestly. But yeah, that does show us what we want it to do. The other reason that this works is if I set up 3 over 9 equal equal to 5 over 15, the means extremes theorem tells me that is going to make 3 times 15 and 9 times 5. I could also set up how does 5 relate to 3 on that triangle equal to how 15 relates to 9. Big to small, big to small. My means extreme. Sorry, I set that up wrong. Did I?
No.
Yeah, no, I set this up right. Yeah, 9 times a 5 and the 3 times a 15. You get the same means extremes. So, yes, that does do exactly what we want it to do. We could write the formal proof, but this is an informal proof of why it works. Does that make sense? Sweet. All right. So, our triangles here, 6, 6, 9, and 8, 8, 12. Let's try Calvin's method. If we relate the long side to the shorter side, what ratio are they in? 9 to 6, right? 3 to 2 or 2 to 3. What about 12 to 8 or 8 to 12?
Same thing.
2 to 3 or 3 to 2. So, according to Calvin's ratio method, this should work. They should be similar. If we check, how does my short side relate to my short side and my long side relate to my long side? Do these come out to be the same? Yeah, 3/4. You with me, Ethan? I know you're probably not feeling well since you just came back from the office. So now we need to prove it. It's like in problem 3. I know my congruent statements. I know my congruent angles. Can I prove this? Carmen?
Or wait. Oh wait, just kidding.
Max?
The triangle is isosceles triangle, so the base angles are congruent.
So, if this corresponds to that side, and that side's congruent to that side, then that side corresponds to this angle, and that must be congruent. So these are the same. So then these are the same. Right? Because angle F is equal to angle J. So then, where do we go from here? Calvin?
Because that makes G and K the same, right?
Why?
The
If we were writing a proof, what would we state as our reason? It's like based on triangle angle sum, right? Because if I know that these pair up and are congruent with these paired up, and I know that this has to equal 180, then based off triangle angle sum, those have to be congruent.
it doesn't feel right. Like, I feel like there's something else that would better explain it, because triangle angle sum is based around the angle measures.
All we're using is that they add up to 180. So what we're saying is this is x, and this is x, and that's x, and that's x. So here I have 2x plus some z equals 180. And here I have 2x plus some z equal to 180. I get rid of my 2x's, and the z's have to be equal. Like z has to be 180 minus 2x on each of these. So, I mean, there might be a different reason we could say it, but triangle angle sum theorem works perfectly fine because it says your 3 angles add up to 180. So then I just show that the z's are equal based off that. And we couldn't use anything like corresponding parts because we don't know that they're corresponding yet. I mean, I really think this is the most efficient.
I just feel like, just from what I know about math, I feel like there should be like some other something.
Yeah. Yeah, don't think it's too. Are you saying you think it's too easy or too complicated?
Well, I just feel like there should be something else that doesn't use the 180. Just that if, say it says if two of the angles on, or if two of the angles of a triangle are congruent to two of the other angles on the triangle, then the third angle will be congruent.
So you could invent a theorem called like the remaining angle theorem, where if I already know two angles are congruent to another two angles, the remaining angle must be congruent to the remaining angle, but that would relate back to the triangle angle sum theorem.
Okay.
So like, yes, what you're saying is perfectly fine, but it all relates back to the triangle angle sum theorem. So I could, like, you could literally write a theorem and call it the remaining angles theorem and use that. And you could just say G is congruent to K because remaining angles theorem. And as long as your theorem was generally accepted, you could use it. So, yes, by rat, we see that these angles are congruent. And then, can we say that these are similar? How? Yes, but what? The what? The angles things? No?
The angle.
Well, okay, you could do angle. But what they're really trying to get you to use here
Oh, it's side angle side.
is side angle side. Put a little sass into it.
Yeah.
It is also angle, but that's lame. Right, yeah, but angle really is angle. Just for redundancy's sake, they get rid of the third one. Now hold up. If we're out of time. All right, get out of here, guys. Huh?
Do we still have to do homework?
Yeah, you should be able to. We'll pick up the notes tomorrow, but you should go ahead and work on it.
Homeworks are pretty easy.
Yeah, it should be fairly easy.
Bye, Mr.
You gotta get out of here. Hasta luego, guys.
Senior math teacher.